What we're going to do is now try to make this a little more easily comparable. We did this before with our solvers, our secant and bisection solvers. We're going to do the same thing here. We're going to try to separate out the problem area, which was this whole thing about fins and heating and cooling and this function and all the rest of it, from the idea of I want to integrate something, and I don't want to care too much about what that something is. So what we're going to do is start off with our code from last class, but first we're going to decide what we actually need. If I'm going to estimate the integral of a function using the left-hand rule, the right-hand rule, so let's sketch out what we're doing here. We got some integral. I want to find this area. What are the ingredients we're going to need? If I say find the value of that integral, what are you going to have to ask me to provide to you? Yeah. Boundaries, absolutely. We need the boundaries. Boundaries. And we're going to call that A and B. That's the classic. So the integral from A to B. Absolutely. What else are we going to need? The function, absolutely. We're going to need to know what we're actually integrating. And again, this goes back to the notation. If I'm going to need to know this, I need to know what the function is. I need to know what A and B is. The last one is the new thing in some sense, because that's enough information here to define our function, and therefore the integral. The last thing we're going to need, because we're going to be doing the left-hand rule or the trapezoidal rule, is the number of intervals to use. And we're going to call that n. So I can choose to subdivide, there's my picture over here, subdivide this into 10 intervals or into 1,000. That's something that we can adapt to, but it'll have to be something specified up front. So I'm going to say, okay, do it with 1,000. What's the area under the graph with that approximation? And that's it. Those 4 ingredients are all we're going to need. So here we're going to do it, and we're going to break off and do a left-hand rule as a separate function. So we're going to go into MATLAB now, over here. And if you look at our MATLAB side of things, there's all this, let me just remind you where we were. This is all about the temperature, blah, blah, blah. And the whole point is we're trying to separate the temperature stuff from the general, let's find an integral stuff. But it's not too badly done down here, actually, because here we had a function. And pretty much from here on in, we had the integral calculation. So what I'm going to do is save this as W72 for a second. And I'm just going to cut and paste out everything that had to do. I'm going to undo that. Let's try that again. Take everything that had to do, and I'm going to do it with a loop because I think it's a little easier to understand. So Control X. I'm going to make a new function called, well, it's going to be called left-hand rule in a second. Total, let's call it I. Left-hand rule of F, A, B, and N. So what we're capturing here in that first line is exactly what we just said. What do I need to evaluate an integral? Someone needs to provide to me, if I'm the function now, the mathematical function, the f of x, the start, the end point, and the number of intervals we're going to use in our approximation. The number we're going to get back, we'll call it I for the integral value, or integral estimate. And most of the stuff we've got here is going to do us just fine. So I'm going to save this as LHR.m in the same directory so we can access it. OK, so there's a couple things we'll need to tweak. Let's see if we can find them together. What elements here aren't quite right? Look for things that have not been defined as part of the input here. L, exactly. Remember, the fin we had was L long, but we're trying to do this generically so we can integrate from anything to anything. What's delta x going to equal? What over n? We have our picture. If I go back to this picture here, how big is each interval going to be? B minus a over n, right. How long is the whole thing? B minus a, start to end, subtract. And then we divide all that into n intervals. So right here we can have delta x b minus a over n. Delta x. OK. So easy tweak to that. That's good. Other things we don't want. Notice n here is highlighted because we don't actually use it because we hardwired it. This is the kind of thing you do when you separate out a first draft of code from everything else. You hardwire some things, then you write it as a function. You realize, oh, wait, no, I want that to be set by somebody else later. The whole point is, when I see this function, I'm going to be handed an n, and I'm going to use whatever n is given to me. It's very close right now, except what value are we handing back? What value is going to be handed back to MATLAB? What letter? I. What letter has never been defined after that first line? I. What did we call it when we first did it? Q. Q, thank you. All right. So we just have to go through and replace all the Q's with I's. And depending on how your interface works, it's actually smart enough, it'll tell you, hey, press Shift-Enter to rename all those Q's to I's. Ta-da. There we go. And if we just look at the ingredients, all right, so I've got delta x is the width of each interval. Good. I'm going to loop. That's good. xi, this part here isn't quite right either. This would start when I is 1. It's going to start at 0, because when I is 1, 1 minus 1 is 0. So I need to tweak that just one little smidgen. Where am I on this diagram when I is 1? The one value that we know is the starting point of the integral, a. The first point that we're at is going to be at a plus no delta x's. So that's what we're trying to capture with this plus, or this I minus 1 delta x thing. This would start at 0, but I don't want to start at 0 anymore. I want to start at a first, and then every other time I'm going to add delta x to that. I'm going to have, on the 5th interval, 5 delta x's. On the 6th interval, 6 delta x's. So we need that a plus. And you can check that by plugging in some numbers in your mind. When I is 1, I'll just have a plus 0. So I'll start at a. The next time when I is 2, I'll be at a plus 1 delta x. So I'll move over one step from there. Now I think we're actually in business. So what we're going to do is tweak our function back here. We're actually going to gut some of this stuff out here. And we're going to say, let's call it L, let's call it I1, is the left-hand rule with our function. Notice we defined a function the line ahead, so that's perfect. We're going to integrate from 0 to L, and we're going to do it with, say, n steps. So I'm going to make n a variable up here. And n error q, and we're going to change that here. We're going to call it I1. We build our function, our mathematical function, some temperature distribution with some constants. And then we're going to say integrate that function over the intervals from 0 to L using, in this case, 100 intervals, and see what error we get. And hopefully, this will run. And it does. And we're just going to repeat what we did at the end of last class, which is notice what happens when we double the number of intervals every time. The error goes down. If I do twice as much work, my error goes down by a factor of 1/2. And that was the rough performance we got before. But now, I don't know. I think it looks cleaner. Looking at this, if I know what left-hand rule does, it integrates. And I know what the inputs mean. It integrates the function from 0 to L using n intervals. I can understand what that whole line is doing much more easily than when it was the loop and all the variables, all the bookkeeping mixed in with the rest of the application.